What is going on, everybody? It's your boy Average Leader here with another video, and today we are tackling number 1837, sum of digits in base k. This question is pretty new and hasn't been asked by any companies just yet, but I can see this one being asked by a few in the future. If you guys can go ahead and hit that like and subscribe button, that would mean the world to me. It helps my channel out a ton by giving it more exposure to people that don't know me. And if you want to see another problem done, just comment down below and I'll make sure to do it for you. And with that all out of the way, here we go. So given an integer n in base 10 and a base k, return the sum of the digits of n after converting n from base 10 to base k. After converting, each digit should be interpreted as a base 10 number and the sum should be returned in base 10. Okay, the thing about some of these interview problems, half the battle is just trying to figure out what the interviewer is trying to tell you. And this is just too much packed into like 2 sentences here. But I think the easiest way to understand this jam-packed problem is by looking at an example and figuring out how they got their output for the given input that we have. And, to make things a little bit simpler, I'm going to do this on the iPad. So let's move over. Okay, so I took this example that we have right here straight off of Leetcode. And remember, what was the question asking us? We had to return the sum of the digits of n, which is this right here, after converting n from a base of 10 to a base of k that we have as our input. Okay, so basically, how are we getting this 9? Well, we're converting n, which is in base 10. So we're going from base 10 to a base k, which in our case is 6. And converting 34, which is a decimal of base 10 once again, to a base of 6, that actually is 54. And I'll explain how we get this in a little bit. But just trust me that we're going from 34 of base 10 to 54 of base 6. And all we have to do from here is just sum all of the digits of our newly converted number to get our output. So here we add 5 plus 4 because those are the digits of our newly converted number. And that gives us 9, which is the answer to this problem. So the real key to solving this problem is understanding what it means to be of base 10 or of base 6 or of base k and converting from one base to another. Because if we can convert from one base to another, all we have to do is just sum up those digits of the newly converted number. Okay, that's what we're doing right here. So what does it mean to be of base 10? Well, that's how all of our numbers are usually written. Like the numbers that we talk about and think about on a daily basis, those are all decimals, or AKA base 10. Okay, and there's a few key characteristics of being a number of base 10, and those are each digit can be one of 10 numbers. Now, for a decimal, what I mean by this is each digit of a number can be any number that's between 0 to 9. I mean, that's how we write our numbers, right? Like, any number can be written with an integer from 0 to 9. Isn't that true? An example would be like, if we had the number 999, with this leftmost 9 being in the ones place, the next 9 being in the tens place, and the 9 after that being in the 100s place. At each individual digit, this one only has 3 digits, right? Each digit can only go from 0 to 9. If I want to go to the thousands place, I can't put a 10 at any of these placeholders, right? That's what I mean by each digit can only be one of 10 numbers, 0 to 9. So this is the first, characteristic of a number being in base 10. And another thing is that, like we have here, every multiple to the left of the ones place is multiplied by 10, or basically by the base that we're in. And an example that we already have up here is that first we have like the ones place right here, then we multiply by 10 to the digit to the left of it, and that we get the tens place, then we get the hundreds place, and if we were to keep going, we'd have 1,000, 10,000s place, and the 100,000s place, and so on and so forth, right? So that these are the two big things that kind of make a decimal or a number of base 10 a number of base 10, without even realizing it. To make sure that a number is actually in base 10, do you know how we would check that? Well, let's just say we had, this number 999, right? The way we check that it's in base 10 and that it's an actual decimal is we would just multiply each of our numbers here by its multiplier on the bottom and just add that number together. So we'd have 9 times 100 equals 900, plus 9 times 10 equals 90, plus 9 times 1 equals 9. And when we add all this up, we get 999. And I'll actually do this with another example just so you guys see which actual 9 this is, which actually 9 that is, and which 9 that is. So if we were to do the same example with this example 243, well, we see that the 2 is in the hundreds place, right? So we'd multiply 2 by 100, and that gives us 200. And we have 4 in the tens place, so we have 4 times 10, and that gives us 40. And we have 3 in the ones place, so 3 times 1 equals 3. And once we add all these things up, we get 243. And that's how we represent our numbers as a decimal, or a number that is a base 10. So, this is really cool. This is all, numbers in base 10. I'm sure this is all stuff that we've seen before. Now, most CS majors, we take a class where we learn about binary numbers. And a part of that curriculum of learning about binary numbers is converting a number of base 10 to a number of base 2, or a binary number. And converting a number from base 10 to base 2 is very similar to what we did before. What I'll typically do when I want to represent a number in base 2 is I'll have all the placeholders written out. So for example, what I mean by that is I'll have all the placeholders written out like this, right? And I would have the multipliers written out for each of these individual placeholders. So like we did for a number in base 10, we wrote the ones place to the far right, right? So I'm going to put 1 right here. And every number to the left of that 1, we multiplied by 10. And then we multiplied that number by 10, and we just kept going on like that. So if I were to do the same thing in base 2 here to represent a binary number, I would multiply each thing to the left of the ones place by 2. So I'd have 1, 2, 4, 8, 16, 32, 64, 128. Now, to convert a number from decimal to binary, we would do something very similar to how we wrote, this number 243. I would just, put each of these numbers in the proper placeholder so that it can be multiplied properly and added properly to get like the number that we're looking for. So, for instance, let's just say I had the number 100, and this would be of base 10. This would be a decimal. Okay. To convert this number to a base of 2, how I would do this is, if I put a 1 right here, that would mean that our number is like at least 128, right? It wouldn't make sense to put a 1 there. An example would be like, if I had like a number in base 10, let's say I were going to represent 1,000 in base 10, right? So we have 1, 10, 100, 1,000, 10,000 here, and then 100,000 here. If I were to represent 10,000 uh, in base 10, I wouldn't put any number in this spot right here, right? I wouldn't put 1 here or 2 or 3 or any number up to 9 in the 100,000s place, right? Because the second I do that, we've made our number at least 100,000, right? Or if I put a 2 here, we'd have to make sure that our number is at least 200,000. But if I were to represent, like, 9,024 or something like that, right? It's a weird 4, but let me rewrite that. 4, right? If I were to represent 9,024, I cannot put a number here, and I can't put a number in the 10,000 place, because if I do that, then, we've instantly made our number at least 10,000. So to properly write this out in decimal, I need to put a 9 here, and then, like a 0 here, a 2 here, and a 4 here. Okay, so the whole point of this is we can't put any number in the placeholders that have a multiplier larger than what our number actually is. So using the same idea, to convert 100 to a base of 2, we shouldn't put any number in the 128 place. Oh, and by the way, since we're in binary, we know that each digit can only be one of 2 numbers now. And when we were in base 10, we had each digit could be written as one of 10 numbers. We can have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But now in binary, we can represent each digit as a 0 or a 1. So at 128, I'm going to put a 0. But now at 64, I'm going to put a 1. Since this is the biggest number that we can represent 100 as. Now, when I do that, I'm going to do this here. I'm going to erase some of this stuff so we have a little bit more space here. Now, when I do that, I'm going to take 100, and I'm going to subtract 64 out of this. And I'm going to get 36 left. Okay? So now, this is the number that we have left to play with. So now when we look at the 32 placeholder, we see that 32 is the next biggest number that we can take out from 36 and still have this number be represented as a binary number. So we're going to put a 1 here instead of a 0, and we're going to subtract 32 from 36. So now we have 4 left. Okay? So now we go and look at the 16. Does it make sense to put a 1 at the 16? No, we shouldn't do that. Because if we put a 1 at the 16, then we need at least 16 left for this to be properly represented as a binary number. So I'm going to put a 0 here, and for the same reason, I'm going to put a 0 at the 8. But look at this. Now we're at the 4 place, right? If I were to put a 1 here, then that would take care of our entire binary representation, because once we subtract 4 from this number, we get 0. And now we're done representing this number as a binary number. We can put zeros for all the placeholders left. And to double check that we converted this number properly into a binary number, we could do the same thing that we did here, where we are multiplying each placeholder by its multiplier and add it all together to see if we get the proper decimal number. So in our case, we have a 1 at 64. So I have 64 times 1 plus, and we have a 1 at 32. So 32 times 1 plus a 1 at the 4 place. So 4 times 1. And if we add this all together, we just get 10, 9, 10, 1. We get 100. So this is how we would convert a number from base 10 to a number of base 2. Now, you can see how tedious this process was right here, right? Now, I gave us an easy number. 100 was pretty easy to represent. It wasn't too bad. But if we had like an outrageous number, like 52,344, something crazy like that, we'd have to be very careful with our multiplier. Like, we'd have to make sure that, 256, 512, 1024, we don't make a mistake while we're making our multipliers, and then, subtracting our number properly, like, how we subtracted here, that we need to do that properly as well. There's a lot of ways we can make a mistake by doing, this type of conversion right here. And, where we're like subtracting from our number to get the proper binary number. But to make things a little bit easier, there is a specific trick out there. All right, and I'm going to show you this trick, and this is how we're going to solve this problem, as well as this trick is what we're going to actually code out. So I'm going to start a new page, and what is this trick? Well, we're going to do the same thing. We're going to convert 100 of base 10 to its binary part, since we know what that number is here. The number that we're trying to get is 0110010. Okay. Now the way the trick works is you need to. Oh, here, let me write this out. Mod by the base you're trying to convert to, and divide by the base you're trying to convert to, and keep doing this until our number that we're dividing is 0. Okay, so these are going to be our 3 steps. Now, what does this mean? So watch this. I'm going to have my number 100, which is in base 10, and to convert it to binary of base 2, I'm going to mod this first by the base that we're trying to get to, so base 2. So I'm going to mod this by 2, and what is that number that we get? We get 0 here. Okay, now the important thing to that I want you guys to keep in the back of your head is we're going to hold all of our modded numbers like in our head. We're going to hold these to the side, okay? And now I'm going to divide 100 by our base, which is 2, and that is 50. So this is the number that we're going to mod next, okay? So, and this is the number that once this turns 0, we're done. So now I'm going to take 50 and I'm going to mod by 2. And once again, we get, 50 divided by 2 is 25. That's a remainder of 0. So 50 mod 2 is 0. Now we're going to divide this by 2 and we get 25. Now 25 mod 2 equals what? This is going to be where we get our modulus, or a remainder of 1. So I'm going to put 1 here. And we're going to do 25 divided by 2, and this equals 12. Okay, so now we have 12 mod 2, and that gives us 0. And then we do 12 divided by 2, and that gives us 6. And now we do 6 mod 2, and this gives us 0. Then we do 6 divided by 2, and that gives us 3. We're almost there. Now we do 3 mod 2, and this gives us 1. Then we do 2 divided by 2. I'm sorry. Then we do 3 divided by 2, and this gives us 1. And finally, we're almost there. Now we have 1 mod 2, and this gives us 1. And then we do 1 divided by 2, and this gives us 0. And now we are done. This is what's going to signal to us that we're done. Now, what I want you guys to do is take a look at all of the numbers that we get left over from our modulus. 0, 0, 1, 1. And assuming that I did this correctly, if we write these modded numbers in reverse, right? What I mean by reverse is, we started, our first modded number is 0, but our last modded number is 1. So if I wrote all our modded numbers in reverse order, you will find that we get the binary representation of this number. So if I wrote this out, I get 1, 1, 0, 0, 1, 0. Okay? And if we look above here, what do we get? 0, 1, 1, 0, 0, 1, 0, 0. If I look here, if I were to add another 0 here, we get 0, 1, 1, 0, 0, 1, 0. This is the exact same number that we got all the way up there, and here, just so you guys can see. I don't know how ugly this is going to become, but I'm going to copy this, and I'm going to put this right here. Look at that. Same. It's the exact, oh boy, exact same number. Okay, isn't that so cool? And look, all we got to do is add on another 0. That's no big deal. I think that's a part of the trick. Just add on one more 0 till the end of that. But we're not asked to, output the converted value, right? All we have to do is output the sum of our converted value. since we have all of the digits of our converted number held after we mod our specific number, and since we just add a 0 to the very end, we just have to have like a running sum the entire time, and just add our modded number to our running sum, and we just output that sum at the very end. So yeah, this is how we're going to do this problem. We're just going to keep dividing and modding our number until we get 0, and we're going to have a running sum that we're going to constantly add to, and we're just going to return that running sum. So yeah, let's move over to the code. All right, who is ready for some code? I know I am. So what I like to do when I start these problems is ask myself, what are we trying to return? Well, we need to return the sum of all our digits after we convert our number from base 10 to base k. So I'm going to have a sum variable that I'm going to return at the end, and I'm going to initialize it to 0. Okay, so after we're done with our problem, we're going to return our sum. All right, now remember, what did we do? We kept dividing our number n by our base k, right? So when did we know when to stop doing our division? Well, when our number equaled 0, or when we kept dividing our number up until we just didn't have a number to divide anymore because it was 0, that's when we stopped. So I'm going to have a while loop, all right? And I'm just going to say while n is greater than 0, we will keep dividing our number. N equals n divided by k, all right? And what were the numbers that were important for the sum that we're going to return? What are the numbers that we kept adding to our sum, which will be the thing that we return? Well, it was just those modded values, right? So all I'll do is sum plus equals n mod k, which just takes our current number that we're at, and it's going to mod it by our k. And then after we have our current number, that number is going to be just a little bit smaller. It's going to be divided by our k, and then it's just going to keep cycling through up until n isn't greater than 0 anymore. So it's literally just like these few lines of code that we need for this problem. So once I run it, let's see if I didn't make any mistakes here. Okay, great. And I'm going to submit this. Boom! All right, runtime 0 milliseconds, faster than 100% of those online submissions. All right, so that is how you do this problem, guys. And let's talk about the time and space complexity, okay? So our time complexity, this is going to have to be an O of n, where n represents the number of times we divide by k, okay? And our space complexity, since we're not utilizing any extra storage, our space complexity is just O of 1 here, okay? So, I mean, yeah, guys, this is how you do the problem. Very easy. I hope you guys learned, something today, kind of why we represent, decimals as decimals, and how we convert a number from base 10 to a number of any base. Hopefully you guys utilize this trick in the future in one of your classes maybe, or in an interview problem just like this. But anyways, if you guys found any value from this video, go ahead, leave this video a like, subscribe to the channel, and comment down below another problem you want to see me do, and I'll make sure to do that for you guys. But with that all out of the way, I'll see you guys next time.